You'll notice I have two presenters on here. My name first, of course, and then Jeremiah Farrell, who is my mentor. If you like this talk, remember my name. If there's a mistake, that's why I have a mentor. Okay. And the second part of this is called a good joke should not be told too often, and there's a reason for that, actually. I'm interested in the way mathematics works in science, but mathematics is not really the same as science, and science isn't the same as mathematics. The language of mathematics makes our ability to predict and understand the world around us, but mathematics only has to be consistent within itself. In science, we have to, in fact, somehow mirror our thoughts through mathematics so that we can predict other things. So this really all starts back actually with Albert Einstein back in 1905, actually. He wrote 3 papers. And when he got the Nobel Prize, most people think he got it for special relativity, but in fact, it was for overall contributions, and in particular, they note his solution to the photoelectric effect. And when someone had commented to him, this is something I've heard, so this was not, this could be one of these tales that you hear, urban tales. But his response was, a good joke should not be told too often, because it was really the beginning of trying to understand what's going on at the atomic level. And the photoelectric effect, was explained by saying that light acts like particles, and eventually it got to be called photons. And these particles then made perfect sense. It was actually the very simplest way to explain the photoelectric effect. So of course someone thought, well, then we can definitely turn down the illumination on light and have it run through a double slit experiment. And if it acts like a particle, then we should get a different result. If you send a beam of light through a double slit, you'll get a diffraction pattern, as indicated on here, or here's the screen if you're looking at it straight on. Here we're just laying it out so that you can see what's happening on the screen. You get light bars and dark spots. But when you send one photon at a time through a double slit, over time you see the little dots, like it's acting as a particle hitting the screen. But those little dots form an interference pattern. So the question is, and Dirac stated, well, the answer is that the photon interferes with itself. So people have approached this problem of trying to make some sense of this. It's counterintuitive, but that doesn't mean it's illogical. So 3-valued logic first came up, true, false, and maybe. But it turns out that as I worked on that for some time, I came up with a different result. Here's a typical true-false table. And typically it's P and Q, P or Q, P implies Q, and then it's P is equivalent to Q. But I liked having a linear combination of these two gives the P is equivalent to Q. So I kind of like the idea of turning the arrow the other way and using that as my fourth one. And of course, we lay out all the possibilities between P and Q on the left-hand side here. So then the next thing I eventually came to was all I need are 2 dimensions. I need to know whether the particle is going through the left slit or the right slit. So I'll represent in the quantum mechanical type of pattern that people adopt, is it a vector? The right, if it's the paintball is going through the right slit, then that's represented by a 1 in the upper part of this vector, and then the left is, of course, the bottom, the second value in that column vector. And you'll notice that these 2 vectors are orthogonal, so that you have this orthogony problem. I've got them written out here, no big deal. But the quantum mechanical wave particle representation then, instead of putting it on the real axis, I put it on the complex axis. But everyone knows that you can't produce a pure state for the wave function. So I'm following the rules that's been set up for quantum mechanics in that sense. So that means I'm going to need mixed states. The mixed states then take linear combinations of the right and left. And of course, there is no left and right in a complex plane. It's just, you'd think of it as up and down if you'd like. But here's our mixed states. So I have a little bit of my left and right. And I have to put in another root 2 because I want to normalize the wave function. It wants to be, these are probabilities. So the square of this complex conjugate, which would just be the row vector with the number made complex, multiply those together and you get 2, but then you square this also and you get a 1. So that's an orthonormal set. This is orthogonal to that set still. Then I was left with, all right, what are the projection operators that carry me from source to the screen? Because you can't figure out, according to quantum mechanical principles, the trajectory of a particle. Okay, so I want to take that trajectory out, but I want to project where it starts and where it ends. So I created the outer products of the classical right and classical left vectors, so that I end up with a 1 and 3 zeros and 3 zeros, and I just add them together and you get a unit matrix. Okay, makes perfectly good sense. And I use these projection operators for each of these operators and, or, and implies. Construct them. Actually, it turns out once I get to or, once I figured that out, this plus sign I put a circle on, which I'm sure people use it for many other reasons than this one. But it's kind of like the complex conjugate or complex number. It doesn't really mean add these two matrices together. It just means here are the two matrices that make this operator work together. And then one more trick, because I got stopped at that point. I thought, I've got and or figured out, but I don't know the implies. So I went back and looked at the implies, and you'll notice that P implies Q is equivalent to not P or Q. So now I have the or, and all I have to do is do the negation, build my matrix. Also, I have to make sure I get a sign change in here. So I'm not going to bore you with the details, but here's the truth tables coming out. Now you notice this is not the same as the truth tables you had before, because there's some zeros and ones, and where you don't, if you're looking at 0 is false and plus one is true, then you would end up with a true and then 3 zeros down here. But this just says if I start at the left, I end up with it's usually initial and final. You can turn it around if you like. But the left is connected through the and. Yes, left and left. They're going to end up on the left side, right and right. But any combination of beginning and starting, which is not the same, you get zeros for. In fact, you'll notice you get zeros all the way through here. There's the implications are there. I'm not going to give you all the details of this. It took me long enough just to finally convince myself this made somewhat sense. Then when I use the quantum mechanical mixed states up here, I still get, if this vector is the starting place, yes, it gets through. But what it tells me is that I end up with the two pure states now are constructively interfering with one another. So I end up with a 1. And same thing here. Now, if I have this state and this state, they're going to destructively interfere with each other, and you're going to get zeros. And so on with this table. I'm not going to deal with all the details of this. These are the 3 slides I had. I thought that was more than enough to give you a taste. I have given the paper to the gift exchange. So if you found any mistakes here, email me. Okay.
Okay.
Thank you.